I'm going to describe how we generate a temperature mole fraction diagram for a system that has two immiscible liquids, in this case water and normal octane. And this diagram is for one pressure, 1.01 bars. Let's look at the diagram. So this side is pure water, mole fraction of 1. This then is the saturation temperature for water, which means the temperature where the saturation pressure is 1.01 bar. And correspondingly at this side, normal octane. And this point then is the saturation temperature of normal octane. At the high temperatures, this region is vapor. At the low temperature, this region is two liquids. And this temperature corresponds to a temperature where the saturation pressures add up to 1.01 bar. So at about 89 degrees C, P sat for water, P sat normal octane, added together 1.01 bar. So that's the only temperature where you can have two liquids and a vapor in equilibrium. And the vapor then has a mole fraction for water, which is the saturation pressure for water over the total pressure, which is sum of the two saturation pressures. In this region, we have vapor containing both components in equilibrium with normal octane liquid. And so the way we generate this curve, for example, to generate some point on this curve, say 110 degrees, at that temperature, we would look at the mole fraction, let's say, of N-octane, because we have liquid in octane. Well, it's the pressure of N-octane. Since it's liquid present, equilibrium to vapor, it's the saturation pressure divided by the total pressure, 1.01 bar. And so that's how we would generate this curve at different temperatures. We have different saturation pressures. And so as we go to lower temperatures, we have lower saturation pressures, and therefore the mole fraction of N-octane is decreasing, the mole fraction of water is increasing. Correspondingly, over here, this curve, now I'm going to look at the mole fraction of water. Since we have liquid water in this region here, we have liquid water plus vapor containing both components. The mole fraction of water would be the saturation pressure of water, if we pick a temperature like 95, divided by the total pressure, 1.01 bar. And so with a few points, we can generate these two curves. And then at a given point, for example here, this corresponds to liquid normal octane in equilibrium with the vapor containing both components, and then where we are on this curve indicates what fraction of the total mixture is liquid, what fraction is vapor, such that the overall composition is 0.2.